Okay, so now we have this problem where we have a file that has many lines which represent islands. Now, I'm guessing that we want to iterate through this file line for line, where each line represents that island's name and kind of create a link. Well, we want to create a linked list out of each of these lines. Okay, so how will we do that? I'm guessing we open the file, go line by line. Every time we have each line, we'll create a new island struct with whatever this line is as the name, for example. And then default the opens and closes to 9 a.m. and in this case 5 p.m. Why does this do this? Okay. And maintain that node and then set the next pointer for the next one over. So we'll have to keep track of, I guess, two structs at once so that we can set. So we need to keep track of two island structs, a previous and a current. Right, the current is the one that we're going to create, while the previous was the previous island that we had created from the previous line. And then we'll set the previous is next to the current. And then after that, we'll set the previous to be the current and move on. Something like that. Okay. All right. So far we've used a separate variable for each item in the list. But if we don't know how long the file is, how do we know how many variables we need? I wonder if there's some way to generate new storage when we need it. Yes, you need some way to create dynamic storage. All of the programs you've written so far have used static storage. Every time you want to store something, you've added a variable to the code. Those variables have generally been stored in the stack. Remember, the stack is the area of memory set aside for storing variables. So when you create the first four islands, you did it like this. So we created Amity, Craggy, Island Nublar, and Shutter as island struct, and they were all values. Okay, so those values exist in the stack. And whose stack? It'd be probably the stack on the main function. So each island struct needed its own variable. This piece of code will always create exactly 4 islands. If you wanted the code to store more than 4 islands, you would need another local variable. That's fine if you know how much data you need to store at compile time. Okay, so that's the situation. It works, like creating these individually works if we know exactly how many, but if we don't, then we had to solve it a different way, right? And yeah, so that's uh, quite often programs don't know how much storage they need until runtime. If you're writing a web browser, for instance, you won't know how much data you'll need to store a web page until, well, you read the web page. So C programs need some way to tell the operating system that they need a little extra storage at the moment they need it. So programs need dynamic storage, meaning that you can create more data on the fly. You can allocate some memory to store these objects on the fly. So wouldn't it be dreamy if there were a way to allocate as much space as I needed with code at runtime? But I know that's just a fantasy. Okay. So how do we allocate things dynamically? We don't know this. We don't know the number of objects we need. We only know it as we are running the program. So how do we create these on the fly, and where does it go? So that's these objects are created on the fly, and they go into the heap. So in this memory map here, it's, I guess, above the stack, below the stack, below the stack. Okay. So use the heap for dynamic storage. Most of the memory you've been using so far has been in the stack. The stack is the area of memory that's used for local variables. Each piece of data is stored in a variable, and each variable disappears as soon as you leave its function. The trouble is, it's harder to get more storage on the stack at runtime, and that's where the heap comes in. The heap is the place where our program stores data that will need to be available longer term. It won't automatically get cleared away. So that means it's the perfect place to store data structures like our linked lists. You can think of heap storage as being a bit like reserving a locker in the locker room. So yeah, whenever you store something in the stack, let's say you declare a you declare some variable inside the stack. When that function returns or exits, all that memory is blown away. Because every time you make a function call, there's like a little portion of memory in the stack that gets like allocated just temporarily, and you do stuff. And when you return from that function, basically returning from your result, you get the result back, but everything else in that function that you had declared is gone. So if you want to keep all that stuff, you would have to actually allocate or assign things in the heap. So there is a way to do that with an API call called malloc. So first, we get our memory with malloc. Imagine your program suddenly finds it has a large amount of data it needs to store at runtime. This is a bit like asking for a large storage locker for the data. And in C, you do that with a function called malloc. You tell malloc function exactly you tell the malloc function exactly how much memory you need, and it asks the operating system, the OS, to set that much memory aside in a heap. So your malloc will request the operating system to reserve a portion of memory for your program. So the malloc function then returns a pointer to the new heap space. So malloc does return a value. That value is a pointer. Okay. So it's a pointer to the start of the block of memory that the operating system allocated for you. So it's a bit like getting a key to the locker. It allows you access to the memory, and it can also be used to keep track of the storage locker that's been allocated. Okay, so I'm going to try and visualize this. If I had memory and maybe just a bunch of slots here, so addresses, and I'm going to try and label them 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 addresses. If I called malloc, and then there's some arguments here. We'll go through that later. We'll get back an address of where our block of memory starts. So if I ask for, let's say, 3 blocks of memory, right? So blocks, maybe that translates to 3 bytes, for example. Let's say the operating system decides it'll allocate 3 blocks here from 5 to 7 inclusive. So address 5 to 8, basically. What malloc is going to return now is a pointer to 5. Then what we can do is we can use this pointer along with the amount of memory we told malloc to allocate to actually move around in this block of memory. So if we know it's 3 bytes, we can just do 5 address, address 5 plus 1 gets us 6 to access the next piece of data over, or plus 2 to get the second element over. Yeah. So basically the third element in the block. So that's kind of like being able to allocate an array dynamically. Okay. So like if we wanted to allocate, let's say we didn't know this at runtime, and all of a sudden you need to know you need to allocate like 10 int elements, for example. Well, then you can use malloc to actually allocate just enough memory to hold those 10 integers. In this case, 40 bytes, 4 bytes times 10. And you'll get back that starting address of where that block starts. You can start to fill in each block with a specific integer. And you can do that by knowing how much memory you allocated with the address offset here. So I think that's like a path to creating like things like data structures other than linked lists. That is. So yeah, so there's like a whole gotcha to this with malloc. So we had to give the memory back when we're done. The good news about heap memory is that you can keep hold of it for a really long time. The bad news is you can keep hold of it for a really long time. When you were just using a stack, you didn't need to worry about returning memory. It all happened automatically. Every time you leave a function, the local storage is freed from the stack. So every time you return, all the storage all the variables and everything that you allocate just goes away. However, the heap is different. Once you've asked for space on the heap, it would never be available for anything else until you tell the C standard library that you're finished with it. There's only so much heap memory available. So if your code keeps asking for more and more heap space, your program will quickly start to develop memory leaks and then run out of memory. A memory leak happens when a program asks for more and more memory without releasing the memory it no longer needs. Memory leaks are among the most common bugs in C programs, and they can be really hard to track down. So yeah, if you have memory and then you start to allocate blocks of it, actually those stay allocated for the duration of your program. Used memory until you actually exit the program or call free. When you call free, what ends up happening is now the OS will start to clear use of the memory, not really clearing the data itself, but marking it as now available so that you can actually then start to use these blocks of memory again. So if you call malloc again, basically it can potentially return you back a block that you had previously used before, but now it's available for you to overwrite with anything else because anything in there is like considered garbage and available. So the malloc function allocates space and gives you a pointer to it. You'll need to use this pointer to access the data, and then when you're finished with the storage, you need to release the memory using the free function. So the free function takes in, right in here, a pointer. Given that pointer, free will then just start from that starting address and then just slowly just clear away the memory like that. There's like a bunch of other, I guess, metadata around your pointer to let it know how much memory should be marked. C has like it has this bookkeeping that it maintains when you're using malloc to understand how much memory was allocated initially. So it's a bit like handling your locker, or it's a bit like handing your locker key back to the attendant so that the locker can be reused. Thanks for the storage. I'm done with it now. Every time some part of your code requests heap storage with the malloc function, there should be some other part of your code that hands the storage back with the free function. When your program stops running, all of its heap storage will be released automatically. So that's the other way. The other way to free up memory that you've allocated is just to quit your program, to terminate it. But it's always good practice to explicitly call free on every piece of dynamic memory you've created. So let's see how malloc and free work. So we start off by asking for memory by using malloc. The function that asks for memory is called malloc, or short for memory allocation. Malloc takes a single parameter, the number of bytes that you need, and most of the time, you probably don't know exactly how much memory you need in bytes, so malloc is almost always used with an operator called sizeof, like this. So sizeof actually takes in a type. Given some type, it'll return back the number of bytes that the type needs for an individual value. So we need to include this header here in a program called stdlib. And inside stdlib has malloc available for us to use. So we just call malloc with its argument being the amount of memory in bytes you want to reserve, or I guess, yeah, reserve. Yeah. So this amount of memory can be hard coded, or it could be computed by using the sizeof function. And then the argument for the sizeof function will be the type of the piece of data. So that type is then allowing sizeof to figure out how many bytes it needs. And then when sizeof returns that number of bytes, malloc uses that to reserve that many bytes of memory. So sizeof tells you how many bytes a particular data type occupies on your system. It might be a struct, or it could be some basic data type like int or double. The malloc function sets aside a chunk of memory for you. Then it returns a pointer containing the start address. So one thing, again, to remember is that when we call malloc, the return value is the starting address. It's a pointer. It's a starting address to the block of memory that we just reserved. But what kind of pointer will that be? Malloc actually returns a general purpose pointer with the type void star. So it's a pointer to void. So now, here's like example usage of malloc. We call malloc with the size of each island struct as a number of bytes to reserve. So then we'll get back a pointer, and we declare that to be a pointer to an island, which makes sense because the amount of memory we just reserved is a pointer that the amount of memory reserved is for an island. So we need that pointer to tell us where that island starts in memory. So if we wanted 2 islands, we would reserve twice as much memory to hold 2 islands. So this would have been like 2 times size of island. Okay. So then now we free up the memory with the call to free. So once you've created the memory on the heap, you can use it for as long as you like. But once you've finished, you need to release the memory using the free function. The free function needs to be given the address of the memory that malloc created. as long as the library is told where the chunk of memory starts, it will be able to check its records to see how much memory to free up. So that goes back to the bookkeeping thing that I had mentioned earlier. Yeah, so if you wanted to free the memory you allocated above, you do it like this. So we allocated memory using malloc to get a pointer and assign it to p. We can reuse that p pointer as an argument to free, so that it knows, it being, I guess, the C compiler or your OS, to free the memory starting from P. And how many bytes? That's determined by the metadata information that um, C or your operating system. I'm guessing. I'm just gonna say operating system. Operating system maintains. So, and here's like one more thing, like another reminder. It's so important to just free memory you don't need anymore. So if you allocated memory with the malloc and call in one part of your program, you should always release it later with the free function. So okay, now that we know more about dynamic memory, we can start to write some code. Okay. Huh. Oh no, it's the out of work actors. The aspiring actors are currently between jobs, so they found some free time in their busy schedules to help you out with the coding. Whew. They've created a utility function to create a new island struct with a name that you pass to it. The function looks like this. Okay, so this is the body of a function. They'll create this. It's supposed to be creating an island for us and returning a pointer to an island in this case. So given some name, they'll allocate enough memory to represent one island, get back a pointer, and assign that to a pointer to an island called I. Then we just set the properties here, like so, and return that pointer, right? The starting pointer of the island that we just allocated using malloc. Okay, so yeah, this is a new function. This is the name of the island, passes a character pointer. It's using the malloc function. So when we call malloc size of island, we're saying size of island. Let's see how big island is. Let's see, what's an easier way to do this? Let's do it this way. We'll have in this case 8 bytes because that's a pointer, so memory address 8 bytes, another pointer, 8 bytes because there's another pointer, and then 8 bytes because there's another pointer. So it's like 32 bytes here. So it's actually 32 bytes malloc allocated, and then we'll get back I, which is an island pointer. So then we will say something like this: if this is like 1 and this is like address, starting address 32, we go all the way to 64 pretty much. And that is basically the memory that we get, and what is returned is I pointing to the first one. And then basically what ends up happening is that it's from here to here, like for example 32 to 40, this is probably going to be the name pointer, and then this one will probably be the opens pointer, and then this one will probably be the closes pointer, and finally we have a next pointer, which points to the next element or the next island. In this case, this one's initialized to null. So this create function will create all this stuff here and return back the pointer to where it begins. Okay. So look carefully at the code for the create function. Do you think there might be any problems with it? Once you've thought about it good and hard, turn the page, see it in action. Well, I see this. Like what they said earlier, if you're going to use malloc, we should consider freeing memory at some point. And I'm guessing that they're calling malloc here and returning the pointer to whatever malloc reserved in memory to fit the island data. there was never free that was called, and I think that's the responsibility of the developer now. So let's see. Okay, so so this actually uses the code. Okay, so we'll find out what's going on. So the case of the vanishing island. Ooh, okay. 11 a.m. Friday. Weather clear. A create function using dynamic allocation has been written, and the coding team says it's ready for air trials. So we have this function that the actors have created, and then it's 14:15, which is 2:15 p.m. The weather is cloudy. Northwest headwind is 15 knots near Bermuda, landing at the first stop. The software team on board providing software. Oh, it's supposed to be like speaking as if it was like, I guess someone controlling a boat. So it's like weather cloudy, northwest headwind 15 knots near Bermuda, landing at first stop. Software team on board providing basic code. Name of the island entered at the command line. Okay, so great. So we're going to enter a name by using fgetS into a name buffer with 80 characters. And then we're going to create, using the create function, an island with a specific name. We'll get back a pointer to an island called p-island0. So far, so good. This here is just basically whatever's returned here. So now we have 14:45. Take off from the landing strip rocky due to earth tremors. Software team still on board. Supplies of Jolt running low. I'm not sure what Jolt is, but okay. 15:35. Arrival at second island. Weather good. No wind. Entering details into new program. Okay, so this is the second piece of code they've entered, and let's just draw this. So we have, in this case, a struct allocated called p-island 0 and name Atlantis. Oops, Atlantis. Okay, now we create another island called p-island1. And what do we call this? Titchmarsh. Titchmarsh. Island. Okay. And then we set p-islands zeros next to be p-island1 with this code here. Okay, so it connects the first island to the second island. This creates the second island. Okay, cool. So far, so good. Back at 1750, basically 550. Back at headquarters tidying up paperwork. Okay, strange thing. The flight log produced by the test program appears to have a bug. When the details of today's flights are logged, the trip to the first island has been mysteriously renamed. We're asking the software team to investigate. Whoa. Okay. Interesting. So what we're getting, when we're calling the print statement with p-island0 as the first one, display. So remember, display is kind of like the helper that we wrote here, except for, well, I guess it's the same property. So exact same function, but yet what's going on is that when we print out this island, we get Titchmarsh, which is the new island that we had created earlier, which is p-island1, so both times. So what happened to the name of the first island? Is there a bug in the create function? Does the way it was called give any clues? Interesting. Okay, so let's go back to create here. So we malloc size of island, call, I name, I opens, I closes, I next equals null, and we return I. We returned I. At that point, that's assigned to p-island. Okay, and then we create a new island, fget s name, sdn, island, p island, create name, and then p island next is going to be p island 0 next is going to be p island 1. Okay, interesting. Huh. So we pass in, I'm guessing maybe the name is wrong. We pass in the name, in this case from this buffer here, create an array to store an island name. Then we'll have the user input the name, and then we'll create it with name as a pointer, so that the pointer to where that occurs in memory. We malloc, return I. Okay, same thing for this one. We again get the name from the character name to the character name buffer, and then we'll call create name again, copy pointer. So basically now we assign that pointer to name. We also malloc too. Interesting. Is it because now what's going on is that we pass a point, since we only have one buffer here, we have one buffer here, we get the name, and then this name is also a pointer. At this point, it's Atlantis. We'll create a node, and then when it's passing, we get the name again, but we're using the same pointer in this buffer here. And then island takes in a pointer. This create takes in a pointer. This name. So we're still passing in that same pace. We're still passing in the same pointer, essentially that character buffer, leading to the allocated place, in memory with currently Atlantis. But now when the user modifies it, it's now Titchmarsh. So then it'll create a node again, but this time this is just a pointer. This island is just a pointer too, right here to name. So it's gonna just assign the address of that buffer into the struct's name property in this case. And that's why I guess is that it's not that there's anything wrong with the creation of the struct, but I'm guessing now that because we're sharing the name uh, addresses, or we're sharing the name data, so that's why they're appearing twice now here, because we overwrote the previous one. So here's what I'm thinking here. So we have our name buffer, and that's like an array, right? So then that points to somewhere here, the data. So let me make that better, actually. Let's just make it simpler and make it maybe 4. So character name starts here at maybe address 100, and then we'll have address 101, 102, 103. And then we also have the struct name. So we'll have, I guess, the first one, P Island 0. We'll make that one blue. And then we'll have maybe P Island 1. Okay? Just never mind this. Anyway, so our function takes in, let's say, user input initially when we want to create P Island 0. Let me just actually also, I want to make this clear. P0, and this one is P1. Okay? Now, when we first ask for user input to our buffer using fgetS, because we had declared it to be an array of 80 characters, let's just say here we have high with exclamation point, and then a null terminating character. Well, when we create the island, this takes in a pointer. So then when we assign this pointer here to a pointer, basically the name of P0, name here, points to this spot. So far, so good. But now we ask for user input again, filling up our array. And this time around, I'll say by. When we create this next struct, again, we'll have a name pointer that points back again to the same array. So now that's why both of them are by in this case, or equivalently now we see Titchmarsh. It's not a good name, but okay. So that's why I think happened. So the case of the vanishing island. What happened to the first name of the island? Look at the code of the create function again. Okay? So again, we're taking in a pointer, but we're assigning that pointer to a pointer of our struct. Okay? So when the code records the name of the island, it doesn't take a copy of the whole name string. It just records the address where the name string lives in memory. Is that important? Where did the name string live? We can find out by looking at the code that was calling the function. So character buffer, we assign data to that buffer, then we create an island struct using a pointer to that buffer. But then that island struct too also has a character pointer or a pointer to a character. And we overwrite again with fgetS, but then we're passing in again that pointer into a character, pointer to a character, which then in that struct, the island struct has a pointer to a character. So they're all pointing to the same, right here, they're all pointing to the same place. So the program asks for the user, the program asks the user for the name of each island, but both times it uses the name local character array to store the name. That means that the two islands share the same name string. As soon as the local name variable gets updated with the name of the second island, the name of the first island changes as well. So, string copying up close. String copying up close. In C, you often need to make copies of strings. You could do that by calling the malloc function to create a little space on the heap and then manually copying each character from the string you are copying to the space on the heap. You are copying each character from the string You could do that by calling the malloc function to create a little space on the heap and then manually copying each character from the string you are copying to the space on the heap. But guess what? Other developers got there ahead of you. They created a function in the string.h header called stirredup. So stirredup. Let's say that you have a pointer to a character array that you want to copy, like this. A pointer to a character S, which has a sequence Mona Lisa. The stirredup function can reproduce a complete copy of the string somewhere on the heap. So this will now create a separate string, a separate sequence of characters in another place in memory containing that same data, and returns back that pointer, the pointer to that first location. So the stirredup function works out how long the string is and then calls a malloc function to allocate the correct number of characters on the heap. That's 10 characters from position S to the null terminating character, and malloc 10 bytes, tells me I've got space starting at the heap at location 2,500,000. So this is a memory address. So then it copies each of the characters to a new space on the heap. So 2,500,000 is an M, 2,500,001 is an O, because a character is 1 byte. So that means that stirred up always creates space on the heap. It can't create space on the stack because that's for local variables. And local variables get cleared away too often. But because stirred up puts new strings on the heap, that means you must always remember to release their storage with the free function. So you have to call free when you're done using that copied string. So that's the thing that you have to remember and take responsibility for when you use stirred up. It's not for free. You can't forget to free it. Otherwise, you'll have a memory leak. And memory leak is when you hold on to memory too long when you don't need it, and it doesn't become available for other things to use. So again, let's fix the code using the stirred up function. You can fix up the original create function using the stirred up function like this. So island, create pointer to an island, create, okay, but everything's the same except for this one. This one will just do stirred up name. So it'll clone the sequence of characters pointed by the name pointer, and then it'll return back the pointer of where that clone starts. Okay, so you can see that we only need to put the stirred up function on the name field. Can you figure out why that is? It's because we are setting the opens and closes field to string literals. So that's why we only need to clone the name. These we don't need to clone because these are all like new strings that we create each time. So string literals are stored in a read-only area of memory set aside for constant values. Because you always set the open and closes fields to constant values, you don't need to take a defensive copy of them because they'll never change. But you had to take a defensive copy of the name array, but because something might come up and update it later. Yeah. So yeah, if the island struct had a name array rather than a character pointer, would I still need to use stirred up here? No, each island struct would store its own copy, so you wouldn't need to make your own copy. So why would I want to use a character pointer rather than character arrays in my data structures? Character pointers won't limit the amount of space you need to set aside for strings. So remember, if you use a character array, you have to know the size of the array you want when you declare it. Otherwise, there won't be enough memory to store whatever string you want to store. So if you use character arrays, you will need to decide in advance exactly how long your strings might need to be. Okay, so that fixes it, I guess. Yeah, right here. Atlantis, Titchmarch. Okay, so now the code works. Each time the user enters the name of an island, the create function is storing it in a brand new string. So let's write that code so that we'll be ready. I'll just put it down here. We'll just copy this here. So we'll have island. It's a function that returns a pointer to an island. It's called create, and it'll take in a pointer to a character called name. And then we'll have a pointer to an island, which is returned by malloc. Give a size of island. That's typical. So allocate the number of bytes a typical island has. So include stdlib.h because that's what we need. And then now we'll go down here. We can start assigning things. Oh, we also need string.h. So okay. Stirred up name opens, and we're using the arrow notation because we're operating on a pointer to some struct. So opens And then next would be null, and we'll return I. Let me just make this better. There we go. So we'll have this create function that creates us individual island structs, okay, or nodes. So now that we have a function to create island data, let's use it to create a linked list from a file. Cool. So here's the basic code. So island start null, island I is null, island next is null. Sure. So we're next would be our current, I guess, and then I would be our previous. Okay. Sure. Yeah, let's do it. So I'm guessing we don't need any of this anymore. Okay. And now let's start typing. So we'll have an island start, which starts out as null. So no memory allocated to this pointer, which points to an island. No memory allocated yet. It's just pointing to nowhere land. So we'll have that with I2, and we'll have that with next 2. We'll also have a buffer to store the name. Basically, as we input, we'll have 80 bytes allocated for us automatically to store the name of the current island we're working with. So if an island's over 80 characters, we're kind of out of luck, but we'll assume that every island's gonna be less than 80 characters. So the pattern here for this for loop is, I guess, while in this case I is not equal to null, I is equals to now next. In this case, we'll want to. That doesn't make sense. Wait. So next is probably going to be our current. So then I will be basically our node that we had created from the previous iteration. Yeah, it looks like it right here. So we want to first initialize next to be create with name, which will create an island struct, and then we'll say if start is null, we'll say start is now going to be next, and then if I is not equal to null, oh, maybe our loop is wrong. Okay, let's say I is now, let's say I is now equals to next. What is this? I and then 2 things here. Hmm. Oh, we do have stuff here. Oh. We should just get. Oh, okay. So maybe this one is fgetS 80 std in, and then maybe not equal to null. I guess. Yeah. So we want to continually get data and put it into name. And fgetS, let's see what fgetS returns us. fgetS will return us back, returns the character read as an returns a pointer to a string that says null on error, or when the file occurs no characters have been read. Okay, so yeah, if we have no more strings to read, then yes, we'll return null. So fgetS will return null. So we want to continually run this loop while fgetS doesn't return us back null. So that's correct. And then x or I will always be equals to next on the next iteration. So next is kind of like a poor way to name this. Next is more like our current, and then I will be like our reference to the previous current that we had from the other iteration. So then what that really means is we had to set this pointer. Then if this is the previous and next is the current, so we had to do x or i's next has to be next, which is reference to this one right here. And then when we're done with that, we do display start. So I'm thinking that's what it is. So again, we declare 3 pointers to an island, start, I, and next. We declare a character buffer with 80 bytes already allocated for us. While we still have some islands to read in from our file, we want to read them into name. We'll get back a pointer to the start of that name. Otherwise, it'll be null. We didn't get anything. And then we'll initialize next, which is going to be the current node, to be a new island with that name passed in. And it so happens that we don't have anything as start yet. We'll just initialize start to be next. Next being this island struct that we just created. So then that'll be like our head node in our list. Our first element, basically. And then if I is not equal to null, what ends up happening now is that we have to maintain that link, right? We have to link the previous node, which is represented as I, to the current node, which is now next. So we'll link them together. And after that, we'll set I to be next, and then iterate again, where we'll create a new next, and then we'll then set I to next again, create a new next, and then so on. And then we'll have basically a linked list. And this runs until we don't get any strings from fgetS. So here's the solution. So fgetS name, okay, now equal null, I equals to next, start equals to next, I arrow next is going to be next, which is this here. And we use arrow notation because this is a pointer to an island, not the island struct value itself, which we use dot notation for. Just want to say that again. Yeah. So we'll save that. Now, okay, well, we're not done yet. Don't forget that if you ever allocate space with the malloc function, you need to release the space with the free function. The program you've written so far creates a linked list of islands in heap memory using malloc, but now it's time to write some code to release that space once you're done with it. Okay, so we have to free every single node when we want to call release. Starting from the start node, we want to go to every single node and release the memory there by calling free. So here's a template that they gave us. So we'll have void release island, pointer to an island called start. So then starting from the start, we want to free that, then go to the next, free that, go to the next, free that, until all our nodes are free. But then we had to maintain, we had to make sure we maintain our links, right? Because if we free start, how the heck are we going to go to the next node? So that's something to think about. So we'll write down this template here, and then we'll have a for loop. So I see what they're doing. So here, look at this. They're assigning the next node first to be the most likely I's next, so that we can maintain that. And then all we need to do is do free I. So we'll take I's next, we'll store it somewhere so that we can get back to it, and then we'll just free that current node, and then we'll probably reassign I to on the next iteration to be this one that we just assigned to, which is next, right? So we'll just do I equals next in this case, and that should actually free every single node until the point where we're at the last node, which is I. So I's next will be null. Next is assigned to null. We'll free that last node, then we'll assign next to I, which is basically null to I, and then the next iteration I will be null, and then we're done. Okay. Is this what it was? Arg! I got tricked. Why? What's going on? Oh, we already have I next. I didn't read carefully. But let's see what they're doing here. I got this one though. Okay, so wait, you're not done yet. Don't forget that if you ever allocate space with the malloc function, you need to release space with free. Okay, yeah. Oh, I see. Because we need to also release the pointer that stores the name because we use stirred up. Because we used stirred up, we allocated memory there, and then we need to free that too. So that's tricky. So actually, we need to free the name because we actually allocated memory implicitly by using stirred up, and we also have to free I too when we're done. Ah, that was a tricky one. All right, I'm glad I got that one. Well, not gotten, but like I understood that one. It's tricky. So I think that's the tricky part about C is that you had to really be careful and remember like what memory you allocated so that you can actually free it later. Because I totally forgot about this. Wow, amazing. Huh. Okay. So yeah, so free the memory when you're done. So after we display our islands, we should release the list that we created. So now that you have a function to free the linked list, you'll need to call it when you finished with it. Your program only needs to display the contents of the list, so once you've done that, you can release it. Okay? So let's just release it right here. Again, since start is a pointer to an island already, this release takes in a pointer to an island. We just pass in start directly like this. Okay, so now we have to run the code. Oh, we need to make our own text file. Okay, let's see. Let's get our text file. Oh, we do a lot today. Um, where is it? Hmm. Okay, did I miss it? Ah, is it this one? Yeah, maybe this one. Ah, we'll fix it. Copy. Uh, here. Okay. So we'll make a new text file. Let's see if we can make it here. Trip one.txt. I think they added a lot more than what we copied, but there will be some more lines after this. Let's just add more. Island of the Blue Dolphins, and then Isla, or let's do Tabor Island, and then let's do Sheena Island, and that's it. Okay, now we'll compile. We'll quit, then we'll do gcc main.c, and then we'll have a.out, pass in trip1.txt as input, and we have our linked list. So we had Delfino, Angel, Wild Cat, Nares Island, Great Today, Island of the Blue Dolphins, Tabor Island, Sheena Island, Open. Okay. Oh yeah, our display was could be. Oh yeah, we didn't have a new line here, so let me fix that actually. And then only by luck we're getting new lines. So I'm gonna fix that. Okay, close enough. Whatever. Okay, so I don't even remember what the display looked like. But okay. Okay, so it works. Remember, you had no way of knowing how long that file is going to be. In this case, because you were just printing out the file, you could have simply printed it out without storing it all in memory. But because you do have it in memory, you're free to manipulate it. You can add in extra steps in the tour or remove them. You could reorder them or extend the tour. So dynamic memory allocation lets you create the memory you need at runtime. And the way you access dynamic heap memories with malloc and free. Cool. All right, we're gonna stop here, but we did a lot again. We learned malloc. We know how to allocate memory, free memory. We actually know how to make a pretty big linked list now, and so I am happy. More linked list and malloc. Actually, not even linked list. It's more like malloc. Anyway, talk to you tomorrow.